Hello, and welcome back to the MIT Integration B 2013 Part 2. In this video, we will solve items 11 to 18. And if you haven't watched it, I suggest you watch the Part 1 where we solve items 1 to 10. I am leaving the link in the description below. So for this video, we will solve these items. So 8 integrals. Let's see how fast we can solve them. Let's start. Number 11. Number 11 is the integral of 0 to pi sine squared x cosine squared x dx. So this is a definite integral, and one common solution to solve definite integrals is using Wallis formula. But the Wallis formula only applies to definite integrals whose limits are 0 to pi over 2. So it looks like this: sine to the m x cos nx dx, where this is equal to m minus 1 times m minus 3 and so on until 1 or 2. And then the same applies for n minus 1, n minus 3 and so on, over m plus n minus 2, so m plus n minus 2, m plus n minus 4, and so until 2 or 1. Then there's a multiplier here. Let's call that alpha. Alpha is equal to pi over 2 if both mn are even and 1 otherwise. So the first objective is to transform the original integral, it's not working, into a form that has limits 0 to pi over 2. We can do this by using the substitution let u is equal to pi over 2 minus x. If we do that, we'll have du is equal to negative dx, and this one becomes 0, pi minus 2 over pi over 2 minus 0. It's pi over 2. Pi over 2 minus pi is negative pi over 2. This becomes sine squared of pi over 2 minus x cosine squared of pi over 2 minus x times negative, let's just make this u, du. Let's interchange u and x, that's fine. Let's put the negative sign here, and we'll have this expression. This is cosine squared of u. This is sine squared of u. So we are left with negative pi over 2 to negative pi over 2 of cosine squared u sine squared u. With this being negative, we can just switch the limits. So this becomes positive and this becomes negative, positive. Okay, next. Note that this is even because both of them have squares. That is f of x, or negative x, is equal to f of x. So a property of even functions is that the integral from negative a to a is equal to twice the integral from 0 to a. It's just sort of symmetry. So this becomes 2 to the 0 pi over 2 cosine squared u times sine squared u du. And this 2 looks familiar. Looks the same. So this one is equal to 2 times 2 minus 1, which is 1. So that's done. The other one and this one, 2 minus 1 over 2 plus 2 plus 2 plus 2 minus 2. And then you can't do anymore, so that's it, times both of them are even, so the multiplier is pi over 2. So this is 1, 1, 4, 2. 2 cancels out, so we are left with pi over 8. Wow. Quite a challenging first question. Okay, next. Of course, what you can do is to find first the antiderivative of this, which is doable if you do power reduction using the half angle identities, but I bet that's longer. So if you're familiar with Wild's formula, this is much shorter. So next, item number 12. So we have to find the integral of 0 to 441 of pi sine pi square root of x over square root of x dx. So this is just 21 squared. And then quite obviously, we use a substitution, let u is equal to pi square root of x, du is equal to pi over 2 square root of x dx. This one as well is your dx, pi dx over square root of x. So this simplifies to 2 du is equal to pi over square root of x dx. So this one becomes, at x equals 0, u is equal to 0. And then at x equals 441, which is 21 squared, u is equal to 21 pi. Okay, so this becomes 2 du. I'll take out the 2. And then this are gone. We're left with sine u du. It's quite straightforward. 2 times integral of sine u is negative cosine u. Then evaluate that from 0 to 2 pi. So that's, 21 pi. So that's 2 times negative cosine 21 pi plus cosine of 0. Cosine of 0 is 1. Cosine 21 pi, this is odd, so this is negative 1. So 2 times 1 plus 1 is equal to 4. Yay! Done. Next, item number 13. Oh, this is quite easy. Integral of tan squared x dx. Tan squared, that's secant squared x minus 1 dx. This we know. The integral of this is, tan x. This is just x. So the answer is tan x minus x plus c. Done. Next. Okay, I'll just use this scratch paper. The next item is, cool, 0 to 256 of x minus floor x squared dx. The floor function, if you recall, finds the greatest integer lower than a number. For example, the greatest integer of 1.1 is 1, 2.9 is 2. Essentially, x is equal to floor x plus the fractional part of x, which we denote as this. This is fractional part. This is floor or GIF. So, for example, for this one, this is, let's just use one. The 2.9. 2.9 is equal to floor of 2.9 is 2 plus fractional part is 0.9. Okay, so how does that help us? This one can be rewritten as x minus floor x is equal to the fractional part of x. Now what's special about the fractional part of x? This is always less than 0, greater than or equal to 0 but less than 1. Okay, so what? So this one becomes 0 to 256 of floor x squared dx. Now note that this is somehow this is always between 0 to 1 regardless of what value of x is. I mean, if that's between 0 to 1, 1 to 2, 2 to 3, and so on, it's always 0 to 1. So we can write this as just 256 times 0 to 1 times the fractional part squared dx. Actually, sorry, make this another variable. Let's say it's u, du, where u is the fractional part of x. Now it becomes independent of x, again, because it's always between 0 and 1. If you don't believe me doing this, you can split this as 0 to 1, and this is, let's just call it f squared dx plus 1 to 2 f squared dx, and so on. But note that f is always 0 to 1 anyway. So this one is just equal to this one is equal to this one. So essentially you have 256 copies of this. So you are left with quite a simple integral, 256 0 to 1 u squared du, which is, by the power rule, u cubed over 3 from 0 to 1 is equal to 256 times 1/3 minus 0 gives you 256 over 3. Finish. Okay. Next. Item number 15. We are looking for the integral of e to the 4th root of x dx. It's quite obvious that we have to eliminate the radical in the exponent. So what we do is we let u is equal to 4th root of x. Actually, I hate it doing this way because I don't like the fractional exponents. So what I usually do is make the substitution u to the 4th equals x instead. And then differentiate both sides. Du, actually 4u cubed du is equal to dx. Then this becomes e to the u, this is u, times 4u cubed du. Okay, next, we simplify this as 4u cubed e to the u du. OMG, this one requires several integration by parts. If you have done integration by parts in class, you are quite certain that this quite takes a long time. The shortcut is using DI table. DI table is the derivative, integral. So you start with u cubed e to the u, then differentiate, 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 integrate, 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 and then plus, minus, plus, minus, plus, minus, and then match it like this. Okay, so the answer to this one is e to the u times u cubed minus 3u squared plus 6u minus 6 plus c. Okay, and then note that I just factored out e to the u. In terms of that x is e to the 4th root of x times, this is x to the 1/4, so this is x to the 3/4 minus 3x to the 1/4 times 2, x to the 1/4, so 2, that's 2/4, which simplifies to 1/2, but let's just make it as is. U is x to the 1/4 minus 6 plus c, and then this becomes 4, I'll just simplify, x to the 3/4 minus 3x to the 1/2 plus 6 x to the 1/4 minus 6 plus c. So this is the answer. Okay. Actually, there is a shortcut to solve this kind of integral, which is quite similar to this one, but I'll reserve that for another video, so stay tuned. Next, item number 16, integral of cos x cot x dx. So as a rule of thumb, when you are lost with trigonometric functions, try to convert all of them, or to write all of them in terms of sine and cosine. So this becomes cos x times Cotangent is cosine over sine. So this is cosine over sine dx. So this becomes cosine squared x sine x. Okay, if I let u is equal to sine x, I need the derivative of sine x, which is cosine x in the numerator. But if I do that, I'll have another cosine x in the numerator, which I cannot integrate, not simply rewrite in terms of sine x. So what we can do is to split cosine squared using the Pythagorean identity. Sine squared x is equal to 1 minus cosine squared x. So this becomes 1 minus sine squared x. Can you see where I'm going? I hope you can. So next I will split this. I will split the numerator, the integrand into 2. That's 1 over sine and sine squared over sine. So that's 1 over sine x dx minus sine squared x over sine x dx. This is cosecant x dx. This is sine x dx. Now this one is easy. This is negative cosine of x. This one is maybe not so easy, but if you have learned it in class, this is just ln of cosecant x minus cotangent of x. So the answer is, so there's a minus here. So ln of cosecant x minus cotangent x minus, it becomes negative negative, so positive cosine x plus c. Done. There are a lot of, by the way, there are a lot of solutions for this one. So you can try your own, but I think this is the most intuitive. Anyway, next, second to the last, item number 17, integral of 2 log x plus log squared x dx. Again, as I mentioned in my previous video, this log x is just ln x if you're more comfortable with that. Okay, so for this one, you might be tempted to evaluate these two integrals separately, but I won't. This is from MIT. This is from MIT, so I'm assuming there's something good about this integrand. And there is. Actually, similar to my reasoning last time about the derivative of a quotient, like this, the low d high minus high d low over low. When you see something as a sum of two terms in the numerator, or actually in the integrand, you should think about the product rule this time. So that's the derivative of fg is equal to f prime g plus fg prime. Okay, so if you let this as, say, one of the functions, f and g, because you have something like this, because you have something like 2 log x, and 2 log x is part of the integral of log squared x. So just to make it clear, what I'm trying to say is the derivative of log squared x is 2 log x times 1 over x. So this looks quite related to this. What's only missing is the 1 over x. What do I multiply with 1 over x to eliminate 1 over x? Yep, that's x. So a quick guess about the function, about the antiderivative is x log squared x plus c. Actually, that's the answer. Let's just check if that's really the answer. The derivative of x log squared x is equal to the derivative of the first, which is 1, plus times log squared x plus the first times the derivative of the second, 2 log x times 1 over x. This is log squared x. This is 2 log x, which is the integrand. Yay! Gets? Gets. Next, number 18, the last one for this video. It's x cubed plus 1 plus x squared dx. I'm not sure about you, but I find it quite intuitive what to do next with this one. Because the degree of the numerator is higher than the denominator, we can write it as something like this over q of x plus r of x over 1 plus x squared. As to how to find this, you can do long division, but I don't recommend that. What we can do is plus x minus x. What? I do that because I want to factor out the 1 plus x squared here. Yes? Yes. Okay. This becomes x cubed plus x over 1 plus x squared dx minus integral of x 1 plus x squared dx. This becomes x times x squared plus 1 over x squared plus 1. This is x plus 1 plus x over 1 plus x squared. This cancels out. This leaves us the integral of x dx minus the integral of x over 1 plus x squared dx. This we know to be x squared over 2. For this one, we let u is equal to 1 plus x squared. Du is equal to 2x dx. So du over 2 is equal to x dx, which is that one. So this one simplifies to 1 over u times 1/2 du, which is 1/2 ln of u. So this is 1/2 times ln of 1 plus x squared. There. So the final answer is this minus this. So it's x squared over 2 minus 1/2 ln 1 plus x squared plus c. Okay? Okay. So that's it for this video, and stay tuned for the last part of this 2013 integration B. See you!